Alright, so in this video, we just want to go over a Chemistry 1010 tutorial sheet 1. This is 2025. So these are the questions that we have. You can see give a name, number of protons, neutrons, and electrons, significant figures, and then we have a question on the isotopes, determining the relative atomic mass, and the question now on the formulas, the question on the number of moles involving Avogadro's constant, percentage of solute in the solution. Okay, so this is a combination of the measurements and then stoichiometry. Okay, so we're going to answer all these questions. Okay, so right now as I'm making this video, there is a PDF accompanying the solutions on our site. Link to that is in the description below. Okay, so let's just get started. Alright, so back to question 1. Give a name and the number of protons, neutrons, and electrons for the following atoms or ions. Okay, so every single time that I'm making a video, I recommend you're allowed to pause the video and just try everything out. Okay, so we'll start with the very first one. So for A, we've got calcium with a mass number of 40. Okay, so I have to give it the name. So that's of course calcium, right? So calcium is a name. And then the number of protons, and then the number of neutrons, and then the number of electrons. Okay, so the number of protons in calcium, of course you can just look at the periodic table, you'll be able to see that. Okay, calcium on the periodic table, these are the details, 40, 20. So the number of protons, therefore, they are 20. Now number of neutrons, when you look at the nucleus consists of the protons and the neutrons. The electrons are found on the shells. Okay, so the number of neutrons is determined as the difference between the mass number, which in this case is 40, minus the proton number, which in this case is 20. So you see that actually we'll still end up with a 20. Now number of electrons depend on the sign. In a neutral atom where there is no sign, the number of neutrons and protons are the same. So therefore we still have a 20 there. Okay, with that understanding, feel free to pause the video and try out the other question. B, which is nitrogen 15. Okay, so nitrogen is a name. Number of protons, nitrogen, of course, if you check the periodic table, it's going to be 7, right? So you've got the proton number of 7. So you've got 7 protons. The neutrons will be a difference between the mass number and the 7, which will give you what? 8 in this case. Okay. Number of electrons, this is a neutral atom, so it's going to be the same as the protons. Okay. Barium 2 plus. Okay. So this is an ion because it's charged, so we'll call it barium ion. Number of protons, so whenever you see a positive there, it implies there was loss of electrons. So the number of protons does not change. That's very, very important to understand. Okay, so you want to look at a periodic table. Look at the periodic table, check where barium is, and then look at the atomic number. So atomic number of barium is 56. So we have 56 protons. The number of neutrons is going to be the difference. The difference between what? The difference between the mass number. So the mass number of barium on your periodic table minus the proton number. Okay, proton number which is 56. Okay, so what you get is a number of neutrons. And then the number of electrons, since we've said a positive 2 indicates that 2 electrons were actually lost. So we said in a neutral atom, if this was neutral, it was going to be 56. Now the fact that 2 electrons were actually lost, that implies the number is going to reduce by what? By 2. So electrons will now be 54. Okay, so I'll leave the last one for you. Please attempt it, compare with the solution provided for in the PDF solution. Okay, simple and straightforward. Now let's look at 2. Question 2, we're just stating how many, and of course we're underlining the significant zeros in the following numbers. So state how many and underline the significant zeros in the following numbers. Okay, so look at the first one. How many significant zeros do we have in the first one? Okay, and then underline. So when a zero is significant, I think that's cardinal for us to understand. Zeros are going to be significant in 2 scenarios. Where when there's a decimal, all zeros that come on the right are significant. Zeros between numbers are significant. Okay, so I think that has given you an idea there. So let's try to do that. For the first one, the zero that is used to show the decimal places is not significant. So there we've got 0. Here how many do we have? So equally there we've got 0, because they are all trying to show where the decimal point is. Okay, so the zeros only get to be significant in a case where if it's 0.4, like that way, that 0 is significant after a number. Okay, no matter how many zeros we're going to have, as long as they are before a number, they are not significant, unless the ones that come after the one there. So this one, that 0 at the end there is significant. Okay, this one, the 0 between, that's significant. Of course I said zeros at the end or after a number, after a decimal point, are significant. So we have 3 significant zeros. Okay, so if you're new to that, you'd want to watch a video where I've introduced all these rules on our site. Okay, so under stoichiometry, you should be able to watch a video where I've explained basically how to determine the significant figures. Okay, now question 3 says, for each of the following quantities, equally underline the zeros that are significant figures, determine the number of significant figures in each quantity, and then determine I think just that. So first of all, we're underlining the zeros that are significant figures, and then also determining the number of significant figures. The difference is here we're stating how many zeros were significant. Now in this other question, we're stating the number of significant figures. So look at let me start first of all with A. A says 0.0030 liters. How many significant zeros do we have there? Can we underline them? So it's a single 0 significant figure there, because from the rules that I gave you in the previous question, only zeros that come after a number after a decimal point are significant. All these ones are not. So 1, and then how many significant figures do we have in total? So the number itself and the 0 will give you 2 significant figures. This one, how many zeros are significant there? So it's only a single 0 between the numbers, so that 0 is significant. The number of significant figures in total are 4. For C, that one is also easy. So only 1 0. The number of significant figures in total, count all the numbers, 1 2 3 4 5. 5 significant figures. Okay. All right. So for D to F, we are taught to express each in the exponential notation first of all. So let me give an example of D. Where do we have our decimal point? So it's there, so we can move it 1, 2, 3, 4, 5. 4.715 times 10 to the power -5, since we've moved from the left to the right. Okay, so do we have any zero there? We don't have any zero, so we can't underline anywhere. Number of significant figures is clearly 4. Okay, so you can do the same for E and F. Yeah, and then pause the video, just try out that, compare your solutions to the PDF solutions provided on our site. Okay, so of course just move a decimal point to that point, and then try to underline a zero that is significant if it is, and then also count the number of significant figures. Do the same for the last one. Move the decimal point from the end to that point, and then tell us the number of significant figures and underline the zeros that are significant. Okay, so solutions are already provided for in the PDF solution, so you just want to compare on our site. So link to that is in the description below. Question 4, we're told silicon is essential to the computer industry as a major component of semiconductor chips. It has 3 natural occurring isotopes, 28, silicon, 29, and 30. Okay, so we're given 3 of the silicon isotopes. So what are isotopes? If I write down the ones we have, we've got 28, got 29, we've got 30. So these are representing the mass numbers. From there we can actually get a definition. So atoms, okay, of the same element with what? Different mass numbers, but same what? Atomic number or the proton number. That's what isotopes basically are. So that's where we start from. So the first thing is determine the number of protons, neutrons, electrons in each silicon isotope. So I've already written them down for you. We can just add the protons there, and then the neutrons, and then the electrons, and so that we can just try to indicate. Okay, so if you check your periodic table, what's the proton number of silicon? So silicon should be 410. Is it 410? So silicon should be 410 if you check your periodic table. Okay, I'm just looking at my periodic table just right now. Yeah, so silicon is 14. Okay, so the proton number is the same. I gave you a definition, so the number of protons are going to be the same. And then for neutrons is now where you find the difference between the protons and the mass number. For the first one, 28 minus 14 is going to be what? What's the difference? 28 minus 14, that's going to be a 14. 29, that's a 15. 30, that's going to be a 16. Okay. And then finally, electrons. So all these are neutral, so electrons are going to be the same with the protons. Okay, so we've seen that where we've got a difference is on the neutrons. Determine the relative atomic mass of silicon. So relative atomic mass is a very important concept under the study of stoichiometry. Okay, so before you can actually do that, you have to know the abundance of all these, which will be given in every assessment. Okay, it's not a need, it's not a necessity for you to know. So silicon 28 the abundance is 92.23%, silicon 29 is about 4.67%, and then for silicon 30 that's like 3.10%. Okay, this is very key, very important. So our formula is very simple. Basically just look at the mass number, multiply by the abundance, which I'll denote by F, and then do that for the second one as well, and so on and so forth. Okay, so for the first one, for example, we have 92.23%, okay, multiplied by 28. That's what you just do, and then add the other one, 4.67%, multiplied by 29, and then add the last one as well, which is 30. So 3.10 over 100 times 30. Okay, that's all you need to do. So you compute now the results. Okay, so for the first part I have 25.8244 plus 1.3543 plus 0.93. Okay, so if you add these values, what are you ending up with? Getting 21.1087, which I can just round off to 28.11. okay, atomic mass unit. So basically this is the relative atomic mass of silicon based off the abundances given and their mass numbers. Alright, so if you're enjoying this tutorial sheet solutions, just wanted to show you that we actually have a site where you can learn all these 4 courses at your own convenient time. Let me show you chemistry, since this is chemistry. So these are the topics that you have access to, from stoichiometry all the way up to organic chemistry. All the lessons are already available for you. Okay, so you can see stoichiometry, for example, from the basic definition of stoichiometry to all the concepts, limiting reagent, combustion analysis. These concepts are covered in our lesson, redox reactions. You can see there are a lot of videos. Okay, all the concentration units, back to iteration. Okay, so not only do we have that, so that's actually applies to all the topics that you're going to learn. Everything is already available for you to learn at your own convenient time. And then we also now have tutorial sheet solutions, of which you can access even the ones from last year, including this very one that you're watching. And then we also have past papers, so you can see the past papers from last year and some other years are available right now, giving you an idea on how questions come during the exam. Okay, so live classes actually have now commenced, so you can actually join our classes via Google Meet, and yeah, get to interact with us and some other tutors in the other courses from Transcended. Okay, so the PDF solutions are now being added on the site. We're trying to automate some quizzes as well to just help you build confidence. Okay, so that's it. I hope you register. Question 5 is very basic. How many milliliters of ethanol are needed to prepare 500 milliliters of the 3.5% solution? What we have in the brackets is indicating to say we are looking at volume, the volume concentration. Okay, so how many milliliters of ethanol are needed to prepare a 500 milliliters of a 3.5% solution? So our solution is going to be, we need the solution to be 3.5%. Okay, so we already have 500, which is the total solution. So what solution should we put on top, which will be able to give us 3.5%, right? Okay, how many milliliters, which I'm calling X, of ethanol are needed to prepare 500 milliliters of a 3.5% volume to volume? The volume to volume just implies we're dealing with volumes there, okay, which can directly actually divide. So we end up with our X to just be 3.5% multiplied by 500, which is just going to be 17.5 milliliters. Okay, that's how simple that question is. Now, one of the simple questions as well is 6. Here we are told to explain what is wrong with the name or formula at the end of a statement. Okay, look at the first one. Barium C2H3O2 2. Okay, so barium diacetate. Is that name okay? No, it's not. So the name itself is just supposed to be barium acetate. Okay, so we don't need to add a di to indicate that there are two acetate ions. Acetate itself is enough. Okay, so usually that is done when you're dealing with a single element. Okay, so barium acetate is enough. Okay, so usually the die would usually indicate would usually indicate a single element anyway, so it doesn't work for the first one. So the correct name is barium acetate. Remove the di. For B, sodium sulfide has a formula that sodium sulfide. If you look at what you're given there, that's what? That's sodium. I'm not writing the formula. That's sodium sulfate. Okay. Now, if we're talking about sodium sulfide, it's a different issue. Sodium sulfide. Okay. So it's involving sodium and sulfide. Now, sulfide should be in group 6, so the formula here becomes 2 instead, sodium sulfide. Okay, so the formula given is sodium sulfate. That's the error. For sulfide, it's this. And then for 3, C, what do you think is wrong there? Ion to sulfate. Let's try to look at that. Ion to sulfate. Okay, so if we pick up the formula for sulfate has got a variance of a 2 as well, right? Okay, so 2 minus. So therefore, if you actually get to combine them, they're just going to be the ratio of 1 to 1. Okay, this is ion to sulfate. This one is wrong. Okay, if we try to split it and exchange the variances, the 3 will go for the ion and then the 2 will go back to the sulfate. It implies that's for ion 3. Okay, so the formula given is for ion 3 sulfate and not ion 2 sulfate. So the correct formula should be this one that I've written down for you. Okay, and then for cesium carbonate has a formula that, is it true? So let's try to observe what's going on. Cesium carbonate. Carbonate, of course, has got a variance over 2. Now, what happens here? Oh yeah, so we don't need the brackets. The brackets are only necessary if there is a subscript down there. So the formula should just be without the brackets. So brackets are not necessary. Okay. That's it for question 6. A very simple question. Now we are on question 7. Watching this video, if you are registered on our site, I recommend you watch a video where we introduce the concept of Avogadro's constant. Okay, so let's try to look into this. Theobromine is a beta alkaloid found in chocolate. Theobromine's molecular formula is that, so despite the name, it does not contain any bromine. Yeah. So A, calculate the mass in grams of theobromine molecule. How many molecules are present in 1 gram of theobromine? How many molecules are there in 1 gram? So at the end of these 5 questions, you're going to understand completely how to use the Avogadro's constant. Okay. So let's start with question 1. We have to calculate the mass in grams of theobromine molecule. Now, if you look at the question itself, we're only given the formula of theobromine, which can easily give us a molecular mass, and we can start with that actually. So we've got C7H8N4O2. We're trying to determine the relative formula mass there. So we've got 2 of oxygen molecules. Look at the periodic table. I'm just using the basic periodic table. 6.00 is enough. Use the provided periodic table. Okay. So for nitrogen, 14.01, and then for hydrogen, 1.008, and then for carbon, 7 times 12.01. So you can just calculate these and sum them up. That's 52, 56.04. 8 times 1.008 is 8.064. That is now giving us 84.07. If you sum them up, 32 plus 56.04 plus 8.064 plus 84.07, getting 180.174 grams per mole. So that's our relative formula mass, or relative molecular mass. Okay. Now the question is asking us to first of all determine the mass in grams. How do we do that? It can be easy if we've got the number of moles, which we don't have. So in instances where the question is this limiting, the Avogadro's constant becomes so useful. So Avogadro's constant is 6.022 times 10 to the power 23 grams, not grams per mole, it's whatever you're dealing with per mole. Okay, so it can be atoms, it can be ions, it can be molecules. Now in this case, calculate the mass in grams of a theobromine molecule. So we're going to say molecules per mole. We've got molecules, that number of molecules per mole. That's very, very important. Okay. So with that understanding, let's use dimension analysis by looking at the dimensions and try to see what's our goal. Our goal is to get the grams. So we've got 180.174, then we've got grams per mole, Okay, so I want to deal away with the moles, so I want to multiply by a reciprocal of this. So the moles can be on top, so we're going to have 6.022 times 10 to the power 23 molecules. Okay, and then per mole. Okay, I've just swapped them. I'm just multiplying by the reciprocal, so that deliberately the moles can actually divide, so that we can just remain with grams. So 180.174 grams multiplied by that. So essentially we're ending up dividing the numbers. That divided by this. Okay, giving us 2.99 times 10 to the power negative 22 grams. Okay, grams per molecule. So I said ethiobromine molecule, so which is just even not necessary. Okay, so that becomes our answer. So yeah, we've answered the first question. We've seen the use of Avogadro's constant. Whatever units you're dealing with, maybe atoms, maybe molecules, ions, supposed to be per mole. And then for B, how many moles of molecules? Yeah, how many moles of molecules are present in a gram of your bromine? How many moles of molecules? So here we now want to find the number of moles of molecules that are present in a gram of the theobromine. Okay, so we are given the mass there. Take note, the mass is 1.00 gram in this question, and then we did calculate the relative molecular mass of theobromine. I think that is sufficient information to help you determine the number of moles, right? So therefore, how do you use this? We want to find the number of moles. So moles should be on top. So you can write the reciprocal of that. So 180.17 grams per mole multiplied by 1.00 grams. Deliberately so that the grams can divide. So in short, we're just dividing a 1 by the 180. So you end up with 0.00555 moles. Okay. Basic calculations of stoichiometry. See how many molecules. So whenever you're trying to determine any number, it may be molecules, atoms, ions, the Avogadro's constant comes back to you. Okay, very simple and straightforward. So Avogadro's constant is 6.022 times 10 to the power 23. Okay, in this case we're dealing with molecules, so molecules, I said per mole always. So how do we find the number of molecules? The only way we can find the number of molecules is by cancelling out the mole, so implying we are supposed to multiply by the number of moles, which we've calculated from the previous question, right? Okay, which was 0.00555 moles. So the moles we get to divide. So then we multiply the Avogadro's constant by 0.055. So I'm getting 3.34 times 10 to the power 21 molecules. Apply the same concept to D now. D now requires you to be a little bit smart about it. This is 3.34 times 10 to the power 21 molecules of theobromine. So C7H8N4O2. We've got that number of molecules. Now we want to determine the number of nitrogen atoms. Now we know that in each of these, how many nitrogen atoms do we have present? 4. So how about in the total number of all those molecules? How many can we have? So you see that the calculation there would basically be very simple. Okay, so if we are saying a molecule 1C7H8N4O2, okay, has got, in fact it would be better actually if we can have it even as the numerator. Okay, so we've got 4 nitrogen atoms per single molecule of that. Okay, how about if we get to have, let's say x we don't know, and then this number 3.34 times 10 to the power 21 molecules or that. So at the end of the day, all we just need is just to end up multiplying by 4. So it's just going to be 4 multiplied by that. That's how you get the total number of nitrogen atoms to be present. So I'm getting 1.34 times 10 to the power 22 nitrogen atoms are present in the 1 gram of your bromine. Previously we did determine the number of molecules. Now we've determined the number of atoms in that gram of molecules again. Previously we determined the number of moles, which helped us determine the number of molecules. And then finally, E, feel free to pause the video and try it out. What is the mass percentage composition of your bromine? What is the mass percentage? So mass percentage, you compare the mass of each atom with the total molecular mass. Okay, this is a very basic question. Feel free to pause the video and just try it out. To give an example of carbon, how many carbon atoms do we have? We've got 7 of them. Multiplied by the molar mass, 12.01 grams per mole, divided by the total mass of the entire compound, the relative molecular mass, which is 180.174 grams per mole. Okay, multiplied by 100. So that will give us the mass percentage of carbon. Okay, so it's 46.6% of carbon. Okay, this is how much carbon it contains in terms of mass by percentage. So do the same now for the remaining atoms. I want you to do for hydrogen, nitrogen, and oxygen, compared to the solutions provided for in our PDF on our site. Now question 8. In clinical situations, the concentrations of solutions are generally expressed as mass percentages. A solution is made by dissolving. So this is similar to the previous question, the last part of this previous question. Now here we are told the concentrations of solutions are generally expressed as mass percentages. Okay. A solution is made by dissolving 1.35 10 to the power 4 milligrams of glucose, which is a mass, in 0.10 kilogram of water, which is the mass of water. What is the mass percentage of solute in this solution? So our solute is a glucose, which is 1.35 times 10 to the power 4 milligrams, and then we've got our water, which is 0.100 kilograms. So feel free to pause the video and just try to determine the mass percentage. Okay, hoping you have. So basically the concept is very simple here. You have to ensure that each time you determine the mass percentage, the unit should be the same. Okay, so we can just convert to grams each one of these. So milli is 10 to the power negative 3, 1.35 times 10 to the power 4, now times 10 to the power negative 3 grams. On the bottom, 0.100 kilogram is a positive 10 to the power 3, so we have grams now. 4 plus negative 3, that will just give us a 1, right? Okay, So which would actually just end up to be 1.35 times 10 to the power 1, which would just end up giving us 13.5 grams over. We can move a decimal point 3 times, 1, 2, 3, so just 100 on the bottom. Okay, now the grams can divide, multiply by 100. So basically we can see the 100 will divide, so it just end up with 13.5%. Okay, that's how you handle question 8. Now question 9, phenanthrene is a hydrocarbon, so implying it's only made up of hydrogen and carbon. A compound only consisting of carbon and hydrogen. If you burn 0.215 grams of a compound, so we're given the mass of that 0.215 grams, okay, and find that it produces, so we're giving us the mass of carbon dioxide and the mass of water. We have to determine the empirical formula of the compound. Okay, so this is combustion analysis. Okay, yeah, there's a part for burning there if you burn that. So we've got CH of the mass 0.215 grams. Of course, after we burn it in oxygen, that is, it gives us carbon dioxide and water. This is combustion analysis. A lot of questions are answered on our site. You can use the link in the description below to just go to our site and learn this entire topic from scratch and look at the full Stoichiometry solutions. So the mass of carbon dioxide is 0.747 grams according to the question, and then water it was 0.109 grams. The total mass was 0.215 grams. So basically the good part is we are from dealing with mass percentages, so it's very easy for us to determine the mass. Okay, so we're only interested in this case, we're only interested in carbon and hydrogen. The other cases, if you check our site, the other cases where the compound can contain carbon, hydrogen, and oxygen, or even carbon, hydrogen, and oxygen, or even chlorine. Why am I just putting oxygen there? Or it may be nitrogen as well. So how do you handle all those kind of questions? Okay, you can actually go to our site. But then in this case, we're only interested in carbon and hydrogen. So we have to find the mass of carbon and hydrogen. So for carbon, carbon over the carbon dioxide multiplied by the mass. Okay, how do we do that? So we know that if you look at our carbon on the periodic table, don't forget about our molar mass. So we just have 12.01 grams per mole. And then on the bottom we are trying to put for the entire carbon dioxide. So carbon dioxide is having the carbon plus the 2 oxygen atoms. Okay, which of course would be 16. And then when you add, in short, the relative molecular mass of carbon is approximately 44 grams per mole. Okay, so that would give us the mass of carbon. So 12.01 divided by 44 we'll end up with something like 0.204 grams. So that's the mass of carbon. So carbon mass is 0.204 grams. Now we can try to find the mass of our hydrogen. How do you do that? Please feel free to pause the video. We've got 2 hydrogen atoms over the total water molecule. Okay, so that would imply we have 2 multiplied by 1.008 over the total relative molecular mass of water, which is just 18.01 grams per mole, multiplied by the given mass of water. So we're using the ratio of the number of hydrogen atoms compared to the total relative molecular mass multiplying by the given mass. Okay, so the mass now that I'm getting of hydrogen is 0.012 grams. Okay, can even remove all this. So we have carbon and hydrogen. The masses we've determined are 0.204 grams and 0.012. So the work of combustion analysis is just to help us find the mass of carbon and hydrogen individually and any other third atom in cases of other elements being present. Okay, so now that we've got our masses, we can actually determine the number of moles. How do we determine the number of moles? By dividing by the molar masses. So 12.01 grams per mole, and then 1.008 grams per mole. Okay, so grab your calculator there. I've just got mine. 0.20 factor except to 0. 0.204 divided by 12.01. Okay, so I have 0.1698858 moles, and then on the other hand we have 0.012 divided by 1.008. Okay, so end up with 0.01190,476 moles. Okay, so now these are the number of moles. You have to look now for the one that's smaller. Okay, which one is smaller between the two? So the one on the right. Okay, so I can divide by the smaller one. Okay, which of course would give you a 1. So let's do that. We see what we're going to get. 0.0169858 divided by 0.01190,476. Okay, so I'm getting something like 1.42. Okay, so I'll just pick 1.4. Let me do this. So we have 1.4, there we have a 1. Okay, so how best can we deal with these numbers here? What if we multiply by 10? We'll end up with 14 and then 10. Common factor, divide by 2, end up with 7 and then 5. Yeah, that's the best way. So that you end up with 7 and 5. Okay, so we don't do what you used to do in high school where you just say no, 1.4 rounded off is 1, so yeah, in the ratio of 1 to 1. No, here we actually do something to ensure that we get the best ratio possible. Okay, so this is the empirical formula of a compound C7H5. Okay, there may be some other interesting questions where they ask you to find from the empirical formula you go now to what we call the molecular formula, while they actually give you the relative molecular mass and then ask you to find the formula, the molecular formula itself, meaning that you actually show the exact number of atoms of each element that should be present. Okay. Now taking you back to our story sheet, so we're just on question 9. We've got question 10, question 11, question 12, 13, 14, 15, 16, 17. So the question actually that I'm talking about is this one there. Okay. So basically, you want to understand obvious questions, limiting reagent, percentage yield, all the other questions answered in this tutorial sheet. If you want to have access to our solutions on our site, please register using the link in the description below. Okay. So if you are facing challenges to register, you can WhatsApp the number given in the description below as well. Alright, so if you are enjoying this tutorial sheet solutions, just wanted to show you that we actually have a site where you can learn all these 4 courses at your own convenient time. Let me show you chemistry, since this is chemistry. So these are the topics that you have access to, from stoichiometry all the way up to organic chemistry. All the lessons are already available for you. Okay, so you can see stoichiometry, for example, from the basic definition of stoichiometry to all the concepts, limiting reagent, combustion analysis. These concepts are covered in our lesson, redox reactions. You can see there are a lot of videos. Okay, all the concentration units, back to iteration. Okay, so not only do we have that, so that actually applies to all the topics that you're going to learn. Everything is already available for you to learn at your own convenient time. And then we also now have tutorial sheet solutions, of which you can access even the ones from last year, including this very one that you're watching. And then we also have past papers, so you can see the past papers from last year and some other years are available right now, trying to giving you an idea on how questions come during the exam. Okay, so live classes actually have now commenced, so you can actually join our classes via Google Meet and yeah, get to interact with us and some other tutors in the other courses from Transcended. Okay, so the PDF solutions are now being added on the site. We're trying to automate some quizzes as well to just help you build confidence. Okay, so that's it. I hope you register